Welcome back. We talked about the theory, the fundamentals behind the circuit, RL circuit, RC circuit. In order to strengthen this understanding, I would like to go and have a number of examples solved on the board for you. Then I'm going to go and perhaps have a couple of examples, if I have time, from RC or RLC. Then I'm going to go and talk about tau and what tau means to us. Here is the example coming from page 263. That's a practice problem. The first thing I'm going to see, first, you have an inductor and only one, so that's first degree. You have a current source, and that's a DC current source. You have a switch. One thing for sure is that this is not practical because you have a current source, and as soon as you cut this open, this current source has to have a way to go somewhere. So this circuit has some technical issues, but that's not of a concern to us. Take a look at this. The voltage of this 2 ohm resistor is the variable of interest. Remember what we said, you can't trust VO of 0 minus because that's not transferable. All I can do is to find, for example, this current and then transfer it to the next stage. So what do? We start systematically. The beauty of the steps are this. You can do this systematically. Give me the two topologies before and after the switching event. So for t less than or equal to 0 minus. By the way, my critical point is noted on the switch. T is equal to 0. The switch has been closed for a long time, and then the switch opens. That's the way the door is going to open. For t less than or equal to 0, the switch is closed. I have a current source, and safely this time, this current source is going to go in, and it's going to go and have the 1 Henry and 3 ohm. It's going to feed this system, so you have 4 ohm, and then you have 2 ohm. As you can see, I'm not going to label the variable of interest on this one because that's not reliable. All I need to find is this one. So that's what is going to help me to find. Now for t greater than or equal to 0 plus, the switch is open. In order to avoid much of the confusion on the part of the inductor, the current source being open, as soon as you open the switch, obviously the interaction between the current source and this section is going to be stopped. They don't interact anymore. Since this is open, basically this entire segment is going to be removed. I'm going to remove that. My system becomes 3 ohm, and then 2 ohm, and then 4 ohm. And this is my 1 Henry. Now, variable of interest would be this that I want to find. And of course, IL can come in handy to help me. So this is the topology before the switching event. This is the topology after the switching event. Let's erase this. Now, for the before switching event, regardless of the variable of interest, I'm going to find IL of 0 minus. 0 minus would look like a long way compared to minus 2 days. So because the switch has been closed for a long time, the inductor is going to act like a short line. So let's go ahead and have this as a short line. That's 3. And then I'm going to have the inductor, the 2 ohm, the 4 ohm, the current source. Okay. What am I trying to find? I'm trying to find this. And now I safely declare this is IL of 0 minus. It's a pure resistive system now. Now you can see this short is in parallel with 3 ohm. Remember, short in parallel with any resistor is going to be short. Because obviously, least resistance paths. From now on, everything is chapter 4 and chapter 3. So This is 0 ohm in parallel with 3 ohm. I can identify first of all that they are in parallel. Because they are in parallel, this 3 ohm really doesn't matter because the voltage across it is 0. Therefore the current through it is 0, and therefore it seems as if it is open anyway. So that's my system. You need to get exercise enough to be able to go from one step to the next. This is simple. This is a current division structure in my mind. IL of 0 minus is equal to 1 over 2 divided by 1 over 2 plus 1 over 4 times 18. And let's take the common denominator 4. 2 plus 1, that's going to be 3. 1 over 2 times 18. 4 comes on top, that's going to be 2 divided by 3. Again, I'm doing this by manually, but you can obviously do this using the calculator. 3 and 18, that's going to give me 6. 6 times 2, that's going to be 12 amp. IL of 0 minus is going to be 12 amp. Why did I do that? Because I need to safely transfer this to this. Once again, inductor is going to hold this. It's going to hold this current momentarily, as if it is strong, 12 amp. Because of this, as I go to the next stage, I can declare that at 0 plus, I'm going to have IL of 0 minus, and the value is going to be 12. Not only I can do this, but I can also replace momentarily the inductor with a current source, just for that moment, for the moment of 0 plus. So, again, I emphasize, let me put this as big as I can. T as equal to 0 plus, so that I have the picture clear. For 0 plus, I can replace this with a current source. How much that value is, the direction is the same as the direction I chose, that was my selection. The value is going to be the one I discovered through the process of 0 minus. That's going to be a current source. That's 3 amp, 3 ohm. That's 3 ohm. And then you have a 2 ohm. And then you have a 4 ohm. Okay, this is what you want to find. And since this system is dedicated to 0 plus, I'm going to call this 0 plus. Once again, you can see there is no inductor in my structure. All I see are a bunch of resistors and a current source. Now, it's up to you how you want to solve it. Nodal, mesh, superposition, whatever it is. But I can also use my current division principle once again. Take a look at this current source. I want you to take this entirely and rotate 90 degrees. See what happens. Rotate this 90 degrees. That's going to be 3 ohm on one end. Then you can see, just for the sake of seeing this properly, I'm going to go ahead and draw this current source. And then this is going to be my 4 ohm. And if I have this properly drawn, that's going to be my 2 ohm. And polarity is the head of the current source. So this is plus minus VO of 0 plus. So this is that. I simply rotated this. Now, if you take a look at the above, what do you see? You are going to see a 2 ohm and a 4 ohm in series. So you can take this out if you want to, because everything is in parallel now. So I'm going to take this out. That's 12 amp. Then I'm going to see 3 ohm. I'm doing a compression now. I'm going to have a 2 ohm. I'm going to have a 4 ohm. And my voltage of interest is going to be this, VO of 0 plus, again step by step. Obviously, after a bit of an exercise, you don't need to go so detailed in the process. 2 and 4 are 6, 3, 6, 12. They are all in parallel. So if I find this current, and I can find that current through the current division principle, if I find this current, I certainly can find VO of 0 plus. So how much is, let me call this Ix of 0 plus. Ix of 0 plus is equal to 1 over 6, 2 plus 4. 1 over 6 2 plus 4, 1 over 3 times 12. So let's simplify this. This is going to be 6, 1 plus 2, that's going to be 3, 1 over 6 times 12. 6 and 6 is gone, 1/3 12, that's going to be 4 amp. 4 amp is going through this, and 4 amp is going through the 2 ohm and the 4 ohm, and therefore I can declare VO of 0 plus is twice 2 ohm times 4 amp, and therefore this is going to be 8 volt. I did all I could by the book, so the polarity, direction, everything are taken care of. So what did I find? What did I find after so much trouble? VO of 0 plus is going to be 8 volt. First IL 0 minus, then IL 0 plus, then current source, then VO 0 plus. One unknown so far, you found it. I'm going to erase, and then I'm going to attack the same system. This is the system I want to attack. Remember, this is the system I want to find VO of T. Remember, when you replace inductor with a short line, keep your original circuit inside. So my original circuit is inside. Do I need IL of T? I don't really need this anymore. So that's my system. I let this system go for a long time. So when I say a long time, the inductor is going to act like a short line. The resistor is going to be on top, 4 ohm, and this 2 ohm, and the voltage is going to be VO. Because this is a snapshot of the design, at infinity, I'm going to label that variable as VO of infinity. Now take a look. Do you have any source of energy? No. This is 0, this current is 0, this one is useless. This is 0, this current has to be 0, everything is 0. So you can say, since there is no source of energy, VO of infinity is actually 0 volt. VO of 0 plus, VO of infinity, you need to tell me what is my tau. What is tau? Let's not forget what the equation says. The equation says L divided by R. L equivalent divided by R equivalent. So L equivalent divided by R equivalent. Okay? Now, here is another task I have to carry out. I need you to put your 2 feet across the inductor. And I need you to look into the design. That this time, I'm not saying you have to short the inductor, I'm not saying you have to open the inductor, I don't care about it. I simply want you to put the 2 feet across the inductor and look at the design. Tell me how much the inductor sees. Well, you might ask me, so tell me how much R equivalent is from. You might ask me, well, this is the variable of interest. The variable of interest is on the VO. Still, tau is dictated by the inductor. It's dictated by the capacitor. So if you have an inductor here, you just need to tell me how much that R is. That tau is going to be the same. Whether it's IL, V 3 ohm, I of 4 ohm, VO of 2 ohm, it really doesn't matter. Tau is the same for all the variables. So if that's the case, how much it is? I have here, then I don't have the voltage, that's not the concern anymore. If I do have an independent source, I'm going to shut down the independent source. Voltage source becomes short, current source becomes open, but now I want you to pick up this. Now you remember initially back in chapter 2, it might have been difficult for you to see this in parallel, but through the exercise you can see it. If you grab this out, you can see 2 and 4, 6 and 3, 2 and 4, 6 and 3, that would be in parallel. So R equivalent is equal to 3 ohm in parallel with, usually we have 2 lines to show what we mean by parallel. 3 ohm in parallel with 2 plus 4 ohm. So it's going to be 3 ohm in parallel with 6 ohm. And the result is going to be 2 ohm. You go ahead and you calculate the parallel resistance. So how much is my tau? My tau is L, 1 Henry. R, 2 ohm. This is going to be 0.5 second. VO of t is equal to VO of infinity. VO of 0 plus VO of infinity e to the power of minus t divided by tau. That's your variable VOT, and the variable VOT dedicated to the after the switching event. Let's go ahead and pick up one more case and try to resolve that. Okay, let's get to practice problem 280. So this is page 280, and I'm going to have a resistor. I'm going to have a switch. The switch is opening at t is equal to 0. I have an inductor. Ohm, 9 amp. For the sake of simplicity, I would like to find the current of the inductor. So, say this is the current I want to find. Do you have a DC? Yes. Do you have one storage element? Yes. Do you have a switch? Yes. You're in chapter 7. So you need to tell me the two topologies before and after the switching event. The switch was closed for a long time. The direction of this arrow, which is the same direction as the force of my hand, is telling me that the door was closed and I opened it. So for t less than or equal to 0, my critical point, the switch was closed for a long time, so that's the switch, and then I had the inductor, and then 10 ohm, and then 9 amp. Okay, 1.5 Henry. For t greater than or equal to 0 plus, what do I have? The switch is now open, the 5 ohm is actually back in the swing, so this is 5 ohm. 1.5 Henry, 10 ohm, 9 amp. What is my variable of interest? This is the direction assigned to me, and this is the direction assigned to me in terms of IL. That's what I'm trying to find. I drew the two topologies of before and after the switching event. Because I only can rely on the current of the inductor, I'm going to analyze this circuit first and then transfer the reliable source of energy to the next stage. This has been there for a long time. That's the key word. This has been there for a long time. First of all, this short and this 5 ohm, really 0 ohm and 5 ohm. It means 5 ohm really doesn't exist. So before I go and actually talk about the inductor, this shorting of 5 ohm means 5 ohm doesn't exist. That's the first thing. The second thing is this. I said this system has been there for a long time. So when I say for a long time, this inductor is going to act like a short line. That's going to be my 10 ohm, 9 amp. That's it. What am I trying to find? Keep consistency. This IL consistency. IL of 0 minus. That's what I'm trying to find. Once again, we are facing a short line and a 10 ohm. Well, you have a 9 amp. 9 people are coming in. They say resistance in front of them, and they say no resistance to get to the same destination. Obviously, all the 9 goes through that loop, the least resistance path. So IL of 0 minus is a no-brainer. It's going to be 9 amp. Why did I care? Because I want to transfer that one to the after the switching event. This is going to be 0 minus as equal to 9 amp. The task of the circuit topology before the switching event is now complete. Okay. Okay. Here is the case. I have the switching event took place already. I have the new topology, and I want to know IL of 0 plus. I already know IL of infinity. In order to find IL of infinity, I let the system go for a long time. The inductor is going to act like a short line again. And you have 5 ohm, you have 10 ohm, and you have 9 amp. What am I trying to find? I'm trying to find this. Because the snapshot of the design is for infinity, I'm going to label that variable as IL of infinity. Well, we are mature at this stage. We can see 9 amp, we can see 10 ohm, 5 ohm, we can see everything is in parallel. We can also identify that IL is actually going through the 5 ohm. So therefore, IL of infinity, using the current division principle, is 1 over 5, 1 over 5, 1 over 10 times 9 amp. 1 over 5, 10, 2 plus 1, 3, times 9. 10 comes on top, that's 2 divided by 3 times 9. Hopefully I haven't made any mistakes. 9 and 3 times 2, that's 6 amp. You've got yourself IL of infinity. 6 amp. Three unknowns you were supposed to find. IL of 0 plus, IL of infinity, and tau. In order to find tau, you were supposed to find L and R. L divided by R, that's going to be my tau. L I know. This is the circuit I'm trying to find the tau for. L is 1.5 times God. Everything is actually combined to one inductor. Now, what is R? I need you to stand across the inductor and look at the design. This is what I'm asking you to do. I want you to actually stand across the inductor and look at the design. I want you to tell me how much R equivalent is from this point. Now, remember what we said, shut down any independent source you have. This is an independent source, it's very easy to verify. It's the 9 amp, you shut it down to 0, that's going to be 0 amp, it's going to be an open line. So a current source that is 0 is going to be open line. It's very important for you to follow this if you haven't exercised enough. Now you are ready to tell me how much R equivalent is. That's 5 and 10, 15. So how much is my tau? It's going to be 1.5 Henry divided by 5 and 10, 15. And therefore this is 0.1 seconds. What do I have? IL of t is equal to IL of infinity, IL of 0 plus, IL of infinity, e to the power of minus t over 0.1 second. Now I would like to explain what tau is. Remember what we said, tau is a time constant. The reason it's a labeled time constant is, the longer the tau is, the longer it takes for the system to get to the steady state. I'm going to discuss that and show you what that means. Okay? What was the function we had discussed so far? Y of t, the current, the voltage, is y of infinity plus y of 0 plus minus y of infinity e to the power of minus t over tau. Whether this is for an RC design or RL design, that's the type of a function I'm going to see. Let's assume that y of 0 plus is less than y of infinity. You can even assume that y of 0 plus is, I'm just making a special case so that we know what we are talking about. 0, and let's say that y of infinity is going to be 5. Just for the sake of it. What is this? This is a function, that's t. Now, for obviously one thing we hardly mention in the in chapter 7, we hardly mentioned it, is this. We said do the switching and apply this equation for the after the switching event. And we typically say that the system has been in resting mode for a long time before the switching event took place. So truth be told, is actually, this is what it is. If you have everything resting, this is actually what it is. Which means for t less than 0, it's 0. Because everything is resting. That's my special case. Everything is resting, and then the after switching event takes place, and then something is going to kick in. But I don't want to enforce this, as we never did so far inside the class or the examples. Implied understanding. Now, at t is equal to 0, I've got myself 0. Okay? At t is equal to infinity, this one is going to go toward the 0, minus infinity. E to the power minus infinity, this is 0. 0 times the bracket is 0. Y of infinity is left. This is what's going to happen. So if I let the system go, it's going to be a steady state response. It never reaches it, but practically we assume it does, and I'm going to call this y of infinity. This one is y of 0 plus. The level it gets eventually, the red line, is going to be y of infinity. What is this? This is the gap. This is the difference between y of infinity and y of 0. I'm going to go in, well, in this case y of 0 plus is 0, but if y of 0 is here, still the gap would be applicable to this line. So I need you to find me the gap. So I'm going to go and use the blue. This gap is going to be y of infinity minus y of 0 plus, or vice versa. But I'm just going to put in basically an absolute value, and I'm going to call this alpha. Just the gap. Okay? Now, what is tau? Imagine t is equal to tau, this t. Imagine this t is equal to tau. What happens? This one is equal to y of infinity. Well, I'm sorry, it's not equal actually. I should be very careful. I want you to find me y of tau. T is equal to tau. Now this one is equal to y of infinity plus basically y0 plus minus y alpha. Since I put an absolute on this, obviously for this example you can see this is 0. For this one you can see this is 5. 0 minus 5, that's going to be minus 5. So I can actually safely say that this is equal to minus alpha. Because alpha is always positive in my understanding, and in this case it's actually negative, that's why I put minus alpha in. And then e to the power of minus tau divided by tau. Tau divided by tau. T is equal to tau. Because I put t as equal to tau. This is t as equal to tau. So this one is equal to y of infinity minus alpha e to the power of minus 1. y of infinity minus alpha e to the power of minus 1. We got the value is 0.3678. I want to round this up, if you don't mind. I'm continuing this process. It's going to be equal to y of infinity minus alpha. 786 is almost 0.37, if you don't mind. I'm just rounding this up. Okay? In 1 tau, I get to y of infinity minus 37% of alpha. You are an engineer and you're supposed to make sense of the numbers. You are supposed to do that. Now this is y of infinity. Alright? You are telling me find the gap 37% less. That's what you're saying, right? You are saying if this is y of infinity, find the gap, alpha is positive in my process, and give me 37% less. So what you're trying to tell me is this: get me 0.37% of alpha and get yourself to this point. What is this? This is y of infinity, this one. Y of infinity minus 37% of the gap. Because I calculated the gap to be y of infinity and y of 0 plus, I can alternatively go in and say this is 1 minus 0.37 alpha. Right? If you add them up, that's going to be your alpha. If you add this and this, that's your alpha. So, here is the process. Whether you find y of infinity and you come down 37% of alpha, or you find y of 0 plus and you go up this value, which happens to be 0.63 alpha, just subtract this. So, you either come into this 37% alpha less, or you come into this 63% alpha more. You are going to come in the same point. The point hasn't changed. You come in, you hit to this one, and you come down. This is your tau. Because I calculated y of tau. I calculated y of tau. This is my y of t, the red one, and I showed you y of tau. 1 tau is this. In some textbooks, they say in 5 tau, you get 99%, almost 100% of that. But 5 tau is really difficult for us because 99% of alpha is not easy to identify by eyes. Some textbooks argue, go in and find 3 tau. You can play with the tau. Just put 5 tau and see what happens. Put 3 tau and see what happens. You make your judgment. But this is a simple understanding. A simple understanding is, if I put 1 tau, that's this one. Now, so basically what do? I'm going to have the rising signal studied. The gap between the end point of the rising signal and the initial point of the rising signal, that's my alpha. I'm going to find 63% of alpha from the initial point and go up. Initial point and go up. I'm going to come back, hit the curve, come down, that's my tau. Now the longer the tau is, what does it mean? It means if I want to reach the same level, the same height in the signal, the longer the tau is, it means it takes longer time. Take a look. This is what it is. This is my tau now. You see? The same level though. This is my new tau. This is, I'm going to call this tau 2, and I'm going to call it tau 1. If tau 2 is more than tau 1, it means it reaches to the same level a longer time. So the longer the tau is, the harder it gets to the final level. The shorter the tau is, what does it mean? When I have a shorter tau, it means my tau is small. It means I'm going to reach the same level a lot faster. This is, for example, this one. I'm going to reach this because this is kind of shooting in the sky. As it goes in, it's going to go and reach faster. This is going to be my, again, let me draw this by the black. This is going to be my tau 3. And as you can see, tau 3 is smaller than tau 1, is smaller than tau 2. If it is longer, it means it takes a longer time to reach a steady state. If it is shorter, it means it reaches the steady state a lot faster. Tau is, that's why it's called time constant. Tau is an indication of how fast the system is going to respond. So far, I talked about the case when it is a rise time. In order to comprehensively cover this topic, I want to go and study a different case. The different case is still the same, except that the entire scenario is going to switch over. You invert this and you see it the other way around. So let's take a look and see what happens. Okay? I hope everybody is clear on this. Assume y of 0 plus is 5 and y of infinity is 0. I'm just changing these roles and see what happens. Now imagine a case where the initial point is actually more than the final point. When y of 0 plus is actually more than y of infinity. Y of 0 plus, as an example, just 5. Y of infinity is 0. Let me plot this. So this is going to be t, and this is going to be y of t. If you just put these numbers into your equation, what do you get? Y of t is equal to y of infinity is 0, y of 0 plus is 5, and that's 0. So this is 5 e to the power of minus t over tau. This is a very nice function. For t as equal to 0, I'm going to get 5. For t as equal to infinity, this is going to be 0. So I know from high level, I'm coming down to low level. Again, one more time, please forgive me for not mentioning u of t, as I'm focused on t greater than 0. Okay, now if I wanted to plot this using the red pen, I'm going to start from 5 and I'm going to go down to infinity, stabilize at this one. Now here I'm going to have y of 0 plus, and obviously when I get to that level, y of infinity is going to be 0. So this is an indication of y of infinity, but obviously for this example, that's going to be the point. 0, 1, 2, 3, 4, 5, that's 5, and that's 0. Okay? Where is my gap? The gap is going to be between the highest level, the initial value, and the final level, in this case y of infinity. And as you can remember, I said alpha is going to be absolute value. So whether I say y of infinity minus y of 0 or y of 0 minus y of alpha, y of infinity, it really doesn't make much of a difference. So let's do that. Okay. All I need is the gap from the initial point and the final point. Whether they are elevated top or downgraded a bit, I don't care. I just need the gap. So let's take a look at the function and let's see what happens. This time, because y of 0 plus is more than y of infinity, that was my assumption. Because this is more than y of infinity, my y of t becomes, I'm simplifying this, y of t becomes y of infinity. Remember this assumption, please. This is positive, and the number is also positive, so it's going to be plus alpha e to the power of minus t divided by tau. Now I'm ready to replace t with tau. Let's see what happens. For t as equal to tau, this is going to be y of infinity plus alpha e to the power of minus tau divided by tau. Tau gives me 1, e to the power of minus 1. We already know it's about 0.37. So this is going to be y of infinity plus alpha 0.37. Again, my job as an engineer is to make sense of the data. What is this one telling me? This one tells me, find me y of infinity and go up. There is a summation. Go up and give me 37% alpha. Go up. Get me the point. You can also say that since this gap is limited, if I think of this as 37%, I can also think of this as 0.63%. So I've got y of 0 plus, 63% down, or y of infinity, 37% up, you come down, here you hit the curve, you come down, this is going to be tau. So the system is easy. What do I do? If it is a falling signal, I'm going to find the gap. I'm going to find 63% from the highest level down, hit the curve, come down, that's your tau. If it is a rising signal, this is a rising signal. Let's take a look at the rising signal. So that's my rising signal, right? Again, I need you to find me the gap. This is the gap. This is alpha. Go up this time. If you're rising, go up. Rise up. If you're falling, go down. Fall down. If you're rising, go up 63%, come back, hit the curve, that's your tau. If you are falling, come down 63%. I want you to remember that word, that number, 63%. Rising, rise up. Falling, fall down. 63%. Go to the red signal, come back and get the tau. It was interesting, I saw from last week, lab number 4, the majority of a group, the class, were able to actually find it very nicely, very good and close to the actual value. But practically, we do not rely on this curve to find tau. Theoretically, that's fine. Practically, there is an issue. We have an oscilloscope inside the lab, and the oscilloscope is a digital oscilloscope. And in order to do that, it actually has a sampling rate. Because it has a sampling rate, it's going to miss the information between the two samples. Whatever happens between the two samples, it's done. Now, if the sampling begins, I'm just going to go extreme. If the sampling is here and here, I might get this as my 0, but it's not. But the challenge for the falling signal is this. This is a falling signal in a very short manner. With that sampling time I just lost, what I would call as my y of 0 plus might have actually have happened here. You see what I'm saying? Inside this sampling rate, something drastic might have happened, and I might have missed it by the digital scope. That's why for the falling signal, we usually do not rely, it's not accurate. It is going to give you some, but the accuracy or the error is about 20%, which is really big. So for the falling signal, we don't. So if you have RL or RC inside the lab, you better find and focus the fallen rising signal. Because the rising signal is easy. Even if I miss something at the beginning, I really haven't missed much. Because the change is not drastic. This one is really sharp, and I missed it. This one, there is nothing much about it. And of course, there is nothing wrong about the last points. Nothing is going to be mysterious. So if you have RC, you may have to focus on VC, because that's the rising signal. If you have RL, you might focus on IL, because that's the rising signal. So you need to pick up your graph appropriately in order to get the right reading from the oscilloscope. So that's going to conclude the topic of tau. I want to go in, and now that we have understood what RC is and what RL is, I want to solve one RC, just to refresh your memory, and one RL, and then go into the next stage of the topic. For an example, if you remember for RC, we said R represents the narrow corridor and a road filled with the rocks. The higher the R is, the higher tau would be, and it takes longer for the villagers to get to the cliff. So the understanding is relatively friendly and easy to follow. Let's go in, and I want to go and pick up some from the end of the chapter questions and attempt to solve one. Okay, let's go for 754, and I'm going to solve part B. (20 volts, resistor, 40 volts, a switch, 6 ohm. The switch is closing in at t is equal to 0, and you have inductor and resistor. So this one is going to be 2 Henry, and this one is going to be 3 ohm. And the variable of interest, well, very nice, is going to be the current of the inductor. Isn't that nice? It's the easiest one because you don't have to go and play around, replace the inductor with the current source to find the variable of interest at 0 plus. That's why. That's why it is easy. Now, here is the case. The switch has been open for a long time, and as you can see, the force of my hand is coming in and closing in the door. The switch is going to close at t greater than 0. What do I have to do? Simple, systematic. Understanding, you go and watch the YouTube and the notes, you find exactly what they mean. But from robotic sense, you simply apply this. T is equal to 0, minus, and less. The switch is open. Since the switch is open, this voltage source is actually dangling in the space. It's not connected to anything. This one is dangling in space. It's not connected to anything. So what do I have? I'm going to have plus minus 20 volts, 2 ohm, and then I'm going to have 2 Henry, and then 3 ohm. That's my case, and thanks God, I have the same interest in this one. It's going to be IL of t. Since I haven't replaced t with 0 minus, I'm not allowed to replace inductor with the short line yet, because everything has its own price and an own understanding. For t greater than or equal to 0. Now, the switch is closed, and I have this 2 branches, and this, everything playing nicely together. It's going to be plus minus 20 volts, 2 ohm. Everything is in ohm, so I may as well not write the ohm value. This is 40 volts. This is 6 ohm. This is inductor, and 3 ohm. Once again, the current of interest, the variable of interest, is this current. Now I'm ready to ignore this one, because I divided it into before switching event and after the switching event. Okay. Let's analyze this. For before switching event, I want to find IL of 0 minus. Why? It's a reliable variable. I can transfer it to the next stage and utilize it, do whatever I want to do. I need IL of 0 minus. Now I say 0 minus, the switch has been in one position for a long time. So 0 minus is infinity for minus 2 days, and therefore the inductor is going to act like a short line. Then it's going to be 3 ohm. Then it's going to be plus minus 20 volts, 2 ohm. You need to know which short comes from what. Please don't confuse. When I have a voltage source shut down to 0, that's a short. When I say a DC excitation and I let the system go for a long time and I have an inductor, that's a short. So you need to practice. All it boils down is to practice. So this is 3 ohm, 2 ohm, 20 volts. What am I looking for? I'm looking for this direction, and now I'm ready to label this IL of 0 minus. Well, what do you see? You see a 2 ohm and a 3 ohm in series. 20 divided by 5. IL of 0 minus is equal to 20 divided by 2 plus 3. That's going to be 4 amp. I got the juice out of the system for before the switching event, and the juice is this one. Let's erase this. I can safely translate this, transfer this into this one. So I want to say IL of 0 plus is equal to IL of 0 minus as equal to 4 amp. Okay? Here is my design. The demand is find me IL of t for this topology after the switching event. I want to find this. Okay. The variable is IL. I have nothing to worry because IL of 0 plus is already found. I need to find IL of infinity. Then again I say infinity, a long time. Then I need to replace the inductor with a short line. And then come down and make it 3. And this is 40 volts. And this is 20 volts. This is 6. This is 2. With the same direction in mind, I want to find IL of t for t is equal to infinity. That's why I'm labeling this IL of infinity. You can do whatever you like to do. You can apply mesh, you can apply nodal, you can apply superposition, Sternen, Norton, whatever you like. Actually, I can do a source transformation, if you don't mind. I can do a nodal. So basically, if I take this as my reference node, if this is 0, this one is going to be minus 40 volts. You remember this? Plus, minus, plus, minus. So the voltage of this node is minus 40. The voltage of this node is going to be minus 20 volts. And the only voltage I need to find is Vx. One equation, one unknown. Isn't that nice? So it's going to be Vx minus 20 divided by 2 plus Vx minus 40 divided by 6 plus Vx minus 0 divided by 3 as equal to 0. Isn't that nice? So let's take a look at all the Vx's. Vx, I'm going to have 1 over 2 plus 1 over 6 plus 1 over 3. And then I'm going to have, take everything to the other end. This is 0, no worry. That's going to be minus 20 divided by 2 plus minus 40 divided by 6. Okay, this one is going to be minus 10 plus minus 40 divided by 6, or you can actually take the common denominator. This one is going to be minus 60 minus 40, that's minus 100 divided by 6, and I think it's going to be 1.33, right? 13.33. Do you have a calculator? I'm going to divide that, please. So it's going to be 100 divided by 6, 16.66. 16.66 minus 16.66. Now on this side, what do I get? I get Vx. Again, I don't have to do this manually. 3 plus 1 plus 2. 3 plus 1 plus 2, that's 6, that's 1. So you've got yourself Vx as equal to minus 16.66. Isn't that nice? What am I trying to find? I'm trying to find IL. The direction assigned to me is this way. Remember the Ohm law and the force upon it. If the direction is this way, then IL of infinity, or this current, whatever it is going to be this polarity minus this polarity divided by 3. So this is 0 minus the polarity divided by 3. So this one is going to be 16.66 divided by 3, and that's it. I don't have to worry about it. Even if you don't simplify this, that's fine. Still, you can actually utilize this as a fraction. What did you do? You found IL of 0 plus. You found IL of infinity. Then you need to find tau. Let's go and find the tau. Okay. Okay, I'm assuming everyone can pause the clip and see all the calculations. Now I want you to stand across the inductor. Inductor is not short, inductor is not open, inductor is just behind you. I want you to remove it for the time being, and I want you to see what the inductor sees. This is the inductor, right? This is the inductor. I want you to see from this angle and tell me how much R equivalent is. This is the two terminals. Now, I want to see that, and I do have two voltage sources, independent voltage sources. I'm going to shut them down to 0. This is going to be a short line, this is going to be a short line, and my system becomes like this. A short line, then I have 2 ohm, then I have 6 ohm, then I have 3 ohm. Now you can see that if you have any weakness in chapter 3 and 4 before the midterm, you are going to be in trouble. You can see how fast we need you to utilize that knowledge. Now from this, I see 6 and 2 to be in parallel and the outcome to be in series with 3. So it's going to be 6 and 2 in parallel. If you go and calculate that, that's going to be 12 divided by 8. Or it's going to be divided by 4, that's going to be 3 divided by 2. So 6 and 2 in parallel would be 1.5. 1.5 and 3, your R equivalent is 3 divided by 2 plus 3, 1.5 and 3, 4.5. How much is your tau? Your tau is L divided by R. L is, what happened to my L? L was, hold on. L was 2 and R was 4.5. You have all the ingredients to write your equation. Your equation would be IL of t as equal to IL of infinity plus IL of 0, IL of infinity e to the power of minus t divided by this value, which is almost half. So I'm going to say 2 divided by 4.5. You don't have to simplify, that's it is. Now I'm going to tell you a trick. Suppose that I want to find this voltage. Suppose the question says, after you do all the trick and everything, this is a different question by the way. L is equal to 200. But right from the beginning, instead of asking you to find this current, the question is asking you to find this one. Or perhaps this one, or perhaps this current, doesn't matter. It's asking you something else. I show you a shortcut, which is a lot easier sometimes. And that is, ignore this, even to the end. Find this one. Find the current of the inductor. Find the voltage of the capacitor. Then replace this with the current source. Replace this with the current source. How much is that current source? In the same direction you just have, the current source is the function you just found. The current source is going to be IL of t that you just found. This is the function. The function is not a DC anymore. But if I have this as a function in my design, then of course this voltage will 3 times this. Or if you want this voltage, you just have a simple system. You just do node or mesh, whatever you like to do. You find this voltage, you find this current. It's relatively a good shortcut. Sometimes it works faster than the regular one. Now I want to go and solve one RC just to refresh your memory, and then let the rest be for the next stage. we really don't have much of a complexity to challenge you for. I'm going to go in and basically try 7.40 part A. The even numbers, you have the answer at the end of the book. The odd numbers, I'm sorry. The even numbers you don't. So I hope as we progress, all the information would be coming in and you will be able to handle the even numbers as well. So let's take a look at the 7.40. And I'm trying to solve part A. I have a resistor of 3 ohm. A voltage source of 12, another voltage source of 4 volts, 2 ohm, and 3 farad. The switch is shown like this. T is equal to 0. And the variable of interest, funny, is the voltage of the capacitor. Why do I say funny? Because remember, for the capacitor, it's not the current that we rely on. It's the voltage of the capacitor we rely on. For inductor, it's the current of the inductor that we rely on. Capacitor tends to hold the voltage. Remember dV to dt for the capacitor? Because of that derivative, the capacitor voltage does not change drastically. That's why. Okay, I have everything. Now, tell me, what do you see? I see a capacitor and only one, first degree. I see DC inputs. That's good. I see a switch on chapter 7. Okay, I need you to tell me the two topology for 0 minus and for 0 plus. Okay, now for 0 minus, where was the switch? Again, this red arrow is actually in the same direction of my hand. So the switch has been horizontal for a long time, and then the switch moves in to the to latch into the one end of 4 volts. So what is my scenario? My scenario is this. The switch is in this position. This is my switch. I just want to show it to you. And this is 2 ohm. This is the capacitor. And then 12. And then 3 ohm. Don't rush. Don't go anywhere. Just write it down, write the topology, and take your time to be as accurate as you can. So that's T less than 0 minus. T greater than 0 plus. The switch is now latching onto 4 volts. This is the switch. This is going to be 4 volts. This is 2 ohm. This is the capacitor, 3 farad. Again, 3 farad really is big, humongous. So it's just for the fun of the math and exercise. What am I supposed to do? You need to devise a strategy. Remember your chess game. All the time as an engineer, you're trying to do a Sudoku, a chess to play. Now what is this? I need to find the voltage of the capacitor at 0 minus, and then I'm going to transfer that to 0 plus. For capacitor, the rules were different. If I let the system go for a long time, it's the two plates are going to charge up. As they charge up, people stop moving anymore. It's going to act like an open line. When I say leave this to a long time, 0 minus versus minus 2 days, 0 minus is actually infinity to minus 2 days, and therefore this has been there for a long time. If I say it is in the long time, this is going to act like an open line, capacitor, and this voltage is going to be Vc of 0 minus. What do I see? This is open line, the current is 0, the voltage drop here is 0, the voltage drop is here is 0, and therefore this 12 volts is going to dump itself across the open line. That's one way of looking at it. Another way of looking at it is actually to write a KVL law, a mesh. If you write a mesh, since the current is 0, these two resistors don't have any contributions to do, so it's going to be VAB minus 12 as equal to 0, and VAB is going to be 12. Isn't that easy? So that's going to be 12 volts. The job is done for before the switching event. When I go into this one, all I can claim is this. VC of 0 plus is the same as VC of 0 minus, is the same as 12 volts. I'm done with this system. You can see I intentionally erase the complete system because some people go and actually find the tau for the wrong circuit. This is the circuit now you need to find the tau for. That's the reason I erase everything, so that you can focus on the right circuit. Okay, let this system go. You have VC of 0 plus. What else you want to find anyway? You have the VC 0 plus. Let system go for a long time. As the system goes for a long time, capacitor once again is going to act like an open line. So that's going to be 4 volts. That's going to be 2 ohm. And then it's going to be this one. Now I'm ready to label this VC of infinity plus minus. Again, the same concept applies. This is 0, the voltage drop is 0, 4 volt is going to drop itself across the VC of across the capacitor, and therefore VC of infinity, actually I want to write it down here, VC of infinity is going to be 4 volts. Now, the next thing I want you to do is this. I want you to put your feet across the capacitor and imagine capacitor is actually behind you. Then I want you to look into the design and tell me how much R equivalent is. I want you to put the capacitor behind you. I don't want you to open it, I don't want you to close it, I don't want you to do anything. I just want you to find me R equivalent that is seen from the two ends of the terminal. Now, in order to do that, you find all the independent sources, you shut them down to 0. A voltage source shut down to 0 is going to be a short line. And then you have a 2 ohm resistance, and then you have the point of observation. This is A and B. How much R equivalent is? You have only 2 ohm. What is my tau? Remember, tau C is different from tau L. Tau C is R equivalent times C equivalent. In this case, it's going to be 2 times 3. It's going to be 6 seconds. You've got 1, 2, 3 unknowns. And you're set to write me the final equation. That is going to be VC of t is equal to VC of infinity, VC of 0 plus, VC of infinity e to the power of minus t over 6, tau. Tau. Both tau c, tau l, remember, they sit under the t. So that's going to be my system RC. I hope by now everyone has been able to grasp both the theory fundamentals as well as a number of exercises we have carried out last week as well as this week. So everybody should be able to handle the RC/RL. We will have several other tutorial questions later, perhaps next week or the week following that. But now I would like to say goodbye and thank you and see you later.